Okay. Okay. Yeah, so hope everybody can see me, can hear me. Okay, perfect. So yeah, thank you for the lovely introduction. It's really a great honor to actually give a talk in Novi Sad since I'm from here, so and attend this wonderful conference in the first place. So the topic of today would be kind of an introduction to causal inference. I'm going to try to give an overview of, it's a very rich field. There's a lot of things we can talk about it. So I'm going to kind of try to give you an overview of a whole bunch of topics in causal inference, and I'm going to try to do it from an intuitive level, so everybody kind of without any background or with some background would hopefully get something out of it. So kind of the introduction of what is causal inference, I think, starts from the motivation of why we should even care about this in the first place. And I think this very much kind of ties into the idea of what is your scientific goal, or being very precise and really thinking about what do we really want to learn. So I would kind of argue that usually we want to ask causal questions. So a lot of things that interest us across a whole bunch of domains, a whole bunch of fields, medicine, economics, physics, they tend to be essentially causal questions. So not all questions are causal, but when you think about it, we're always interested in kind of how do things work, how can we kind of intervene on a certain process and learn from it. We're not really interested in just the associations. So when you think about this kind of ladder of causation, to say, we kind of go from that lower steps where we're talking about association, correlation, and so on. So it seems like things are connected in some ways. But usually we want to kind of change something and then see if we change something, does it change the outcome? So we're really trying to understand the process. So this is that idea of an intervention kind of comes into play, and that is kind of the cornerstone of causal inference. So now we're introducing something else to that process. We're not just seeing that things are possibly correlated or they're associated in some kind of way. Now we're saying that if I intervene on this system, which implies that I know more about this process in general, if I intervene, can I actually see something happening and I'm really learning about it? So this is where this idea of what if I had done something, how would that change kind of comes into play. So we're going higher and higher up the ladder of causation or understanding it itself. But this is, as you can imagine, answering this type of causal questions is really hard. And as we kind of go through this presentation, you'll see that a lot of it is just being very clear about what is my scientific goal, how do I ask these type of questions, thinking very deeply about the process itself and being very clear about the assumptions and so on. So we'll go through all of this, and hopefully kind of what I hope you would take from this talk at least is that having this type of causal frameworks is a very useful thing as you're thinking about your scientific questions. So this kind of comes to the top, kind of what I just mentioned, that usually we go from this idea of correlation, causation, and then we learn about causal inference, and then you're like, wow, that's an answer to everything, and then you realize that it's not. Like it almost puts us in a perspective of, oh, how little do we know in a sense. So what I mean by hard, so these are just some of the examples of some of the hurdles that we kind of come when we think about causal inference. Usually it's really nice if you have a causal graph, so we can kind of draw what this process looks like and what is connected to what. But then you might ask, okay, so we're drawing a certain graph. Is that an actual true graph? Can we learn something from the data? Can we use something like graphical models for it? Yes, but that also requires some sort of estimation. So there's a lot of uncertainty that kind of pops out in a lot of different places. So. Or you can think that my graph is useful, I have so much domain knowledge, but do you really? Now one would start. So there is a lot of kind of overconfidence in the assumptions that kind of tends to rear its ugly head in these type of problems. There's also the idea of it's really nice if you have a randomized trial. That's usually in causal inference considered like the gold standard of it, where I'm actually manipulating some kind of process and then seeing what is the outcome of it. But even then, there are a lot of problems with it. If you work in the clinical trial literature, it's very difficult to have a trial. But then we also have observational data where we're not really manipulating something. We're collecting data and then trying to learn something from it. And a lot of people would say causal inference, the role of it is to kind of, we have this observational data, and now we're trying to make it almost a randomized trial. So we're trying to replicate kind of a perfect condition under which we would learn something. And then we have, like, is this replicable? Why does my trial not match my analysis results? Does that come from the estimation part, or does that come from that my graph was wrong? So there's a lot of things that can be very problematic. So this is where, as I said, I hope if you get anything from this talk is this idea that thinking about our scientific questions and whatever we're trying to learn, if we use this type of causal framework, it's very useful, but because at least you know what are the assumptions and what do I know and what do I not know. So I like to kind of put it, this is kind of the causal framework tool to say. So what does causality help us with? It helps us, first of all, to frame better questions. So by thinking about what is the intervention, I'm really thinking about what can I actually learn if I manipulate this, would that cause that? So I'm being very specific about the type of question that I want to learn. It also helps us think about the study design itself. Sometimes, as I said, we can have a trial and I can really manipulate it. Often I cannot. But with causality, I can think about what would be an ideal experiment under which I can actually learn whatever I really wanted to learn. So we can kind of pretend with it, and then maybe with some causal tools, we can actually edit whatever process generated data. I can do something to be as close as possible to that perfect trial that maybe I had or maybe I didn't have. I think it also helps us think about, and I pointed in the first one, what can I manipulate? What part of these can I actually intervene on and learn about that part of the process? What's random in it? Where does uncertainty come off? What do I know? What do I not know? That kind of ties into understanding assumptions. So under what assumptions can I actually say that this is not an association that I'm observing? I'm actually have a causal relationship here. And I think the last part then is if we're doing a really good job to getting to the point where we're thinking that, okay, so this is a causal question, I can learn some causality from it. Now we want to do a really good job with estimation as well. It's kind of a pity if you do all this work, you're being very clear of your assumptions, what the question is, what I'm doing, and then I do a really bad job when I estimate something. So that's almost a pity. So for me, causal inference is the whole picture. We're doing a really good job making sure that we're answering the right questions, but we're also doing an extremely good job with the estimation as well. So this is kind of the tie between machine learning, causal inference, and then kind of advances in statistics as well. So hopefully that motivates today's talk a little bit. So let's go a little bit about defining some of the causal language and type of questions we can actually ask. So, and I've alluded to it a little bit, so let's imagine that we have, kind of as an introduction, some kind of a question we're hoping to answer, and we have some individuals and we collect some baseline covariates on them. I'll always call them W in the rest of the talk. And then maybe I'm interested in some kind of a binary intervention here where assigning individuals to maybe one advertisement that has some kind of graphic on it and then another advertisement that has a different type of graphic on it. And as I'm assigning this, I can do this completely randomly where I'm just flipping a coin, or maybe individuals kind of self-select of what they're picking, and so it's kind of observational study. And then maybe I'm interested in something simple like how many times, if I give you this advertisement for whatever, product, movie, whatever this is, how many times did you click on it, how many times did you buy some kind of a product? So then I quantify that. So I'm always going to say baseline covariates, so that's what's collected before, some kind of a treatment A, here it's ad assignment, and then my Y is always going to be the outcome here being how many times you clicked on it. And then the idea is I'll assign you either this one or that one, and then I'll see what your outcome is at the end for each of the individuals. So what's the causal language for a problem like this? This is a very simple problem we might think about. So what causal language lets us is kind of define a target with respect to some kind of a hypothetical experiment. So we're not really interested in just seeing, I assign you this ad, and then I saw your outcome. I want to see if I assign you a different ad, what your outcome would be. So it's almost kind of if you lived in a different world where I assign you something else, what your outcome would be, and that's kind of your individual effect, but we're usually thinking of them on average. So to say this in kind of the terms of causality, we could use different types of framework, and this is where I say that causal inference is a very rich field. We can call them potential outcomes or counterfactual, or define them through structural equations. We can do something like do calculus from Judea Pearl. So there's a lot of different frameworks that would kind of do similar things. So for today, I'll just focus on potential outcomes, but I just want you to know that there's a lot of different frameworks. I don't think one is better than the other. It's just we only have an hour today. So what do potential outcomes look like? So the simplest one would be that Y that we had before, which was the outcome. Now I'm indexed it with an A, and that was an intervention. So that says that this would be my outcome had we set this treatment, that big A, to that small a. So for example, I'm assigning you this ad, what's your outcome? I'm assigning you the other ad, what's your outcome? And this would be an example, because we're in a binary setting, this would be an example of a static intervention. So I'm telling you directly, there's no randomness, you take this ad, and then you take this ad. But we can be kind of more elaborate about this. So we can also have this YDW. So now I'm saying that I'm not really just assigning you this ad, I'm assigning it based on some kind of a function, maybe of your baseline covariates. So maybe your education, your movie interests, your whatever interest. So based off of that, I'm assigning you some kind of intervention. So this is called a dynamic intervention. We can also do something even more elaborate. So I can define something like this YGW. So this is an outcome had we set treatment A to be drawn from some kind of a distribution GW. So why is this useful? This is called a stochastic intervention. This is useful if you're, for example, an application being exposure to some kind of pollutant. So it's very weird to say I'm assigning you this level of a pollutant. That's probably not going to happen. But maybe I have some distribution of this pollutants over a year or something like that in one city and then another city. So I'm saying, like, if I draw some level of it that you were exposed to in this city, right, what will be your outcome, as opposed to if it was drawn from a very highly polluted city, for example. So we can, this is kind of increasing level of complexity in a way. Or we can have more than one intervention. So that's this last one. So now we have a bar on the A. So this is the outcome, and we set treatment to a specific sequence. And then we can have some kind of an outcome at the end, given that you had a whole sequence of different treatments over time. So we can do a whole bunch of things, but the idea is we're always playing with there's some kind of an intervention, some kind of an exposure, action, however you want to call it. And then we want to look at what does the outcome look once we actually do that. So now that we've defined these kind of factual potential outcomes, now we can talk about what we actually want to learn. So these are some examples of what I would say kind of the simple causal inference parameters we really care about. Probably the most canonical one that I'll talk about today, because it has a kind of the simplest results, is called the average treatment effect. And the idea behind it is I'm looking on average, what the kind of the difference in the outcome had I've given a treatment and not given a treatment, right? Kind of average over all the baseline covariates. I can also make it a little bit more complicated by thinking about the conditional average treatment effect. So now I'm saying kind of I'm looking at the same difference on average conditional on some set of baseline covariates. So that's more kind of close in line, right, with the heterogeneous treatment effect. So that's what I'm aiming at. So assuming that maybe on average there's no effect, but maybe with a certain kind of strata of this W, there is an effect. I can think about things like marginal structural models or MSMs. So here I'm looking at, I have a whole bunch of interventions maybe over time, and what I really want to look at is maybe what is the line if I kind of connected all of them. So there's a difference between assigning if I have 5 time points, giving you treatment 5 points as opposed to giving you 4. Maybe there's a difference, maybe there's not. So it kind of creates essentially a line, right, in 2D, and maybe I'm interested in something like the slope or something like that. So that would be an example of it, of course, on average. We can also think about things like those response curves. So now I am kind of indexing by a small a, and this could be continuous, could be a whole bunch of things. So this is actually a pretty difficult parameter. Or I can think about stuff like optimal treatment regimes, where now I'm indexing, so that's the dynamic treatment that I mentioned on the previous slide. So I have some kind of a function of some covariates V's that we had before, and I would like to optimize, maybe maximize our kind of factual outcome under that dynamic treatment. So I'm looking for essentially a function that would optimize this in some way. And then there are many, many more. These are, I guess, kind of the more canonical ones. If you took a class on causal inference, you would encounter. But the idea that I kind of wanted you to get from this is that essentially this causal target parameter, we shouldn't be thinking about it in terms of, I don't know, if you take like a linear regression class, then you're looking at a coefficient, and that's what I'm looking for. No, you should be thinking more along the lines of, if I had an intervention, how would I answer this scientific question? And then maybe some of these, and there's many more, and you can invent your own versions of target parameters that is as close as possible to that scientific question that you're interested in. So that's kind of the intro. So let's talk about, going back to that causal framework that I talked about before, that I think it's quite useful as you're thinking about different problems. So So this is kind of the framework I'll follow today. And the idea is, as I said, we always start with some kind of a maybe scientific question, should be here, and then we are trying to make it a causal question by thinking about it in terms of potential outcomes and so on. And then what we want to do is we kind of want to minimize this causal gap. So we want to be as close as possible to that, whatever we really want to learn, that's the kind of the causal question here. So this is where we use the causal framework. And the idea is that we'll come down to some kind of a causal, what we call target parameter. So you can think of it as kind of a causal estimate. It's going to be some kind of a quantity which is expressed in terms of potential outcomes, like I showed in the previous slide. But when you think about how do I estimate that? What does that mean? Like y indexed by a, like what is that? Where do I get that in my data, right? If you think of it, if you created kind of a, maybe like a graphic, I've observed my outcome for individuals that gotten treatment. But if you gotten treatment, I didn't observe you for when you didn't get treatment, right? That's, like I'm never gonna see that. I can't go back to the past and do it. So we're not really close to the point where we can actually do some kind of statistical estimation. So this is kind of the first, and I'll show you the next slide, what we called the causal part, essentially, is that we're going from really clearly defining what the question is in terms of this causal language. I'm defining it in terms of potential outcomes, and now I'm doing something to make it in a statistical estimate, something that I can actually estimate from the data. So this is where we get to the closest statistical target. So there will be kind of a gap between the causal framework, how I define it, and the statistical one. And then once I get to that point, now I'm kind of in the land of statistics. We're back to kind of, right, what we already know. And now I'm trying to kind of minimize the statistical gap. So there's two gaps here, the causal one, and then there's a statistical one. And now I can use everything that we have in machine learning and everything that we know to kind of estimate something, depends on what I'm trying to learn. And then if I also want to get inference on top of it, we're going to do an extra step, and I'll talk about it at the end as well. So that's kind of the idea of what I called the causal framework. So we can hash out these steps a little bit better. So today I'll talk about these kind of very vaguely 5 steps, and we'll go through them with a kind of an example to see if you actually had a question you're interested in, how you would do this step by step. So all of this is causal inference, and I think this is kind of maybe a point of confusion people sometimes have, but technically the first 3 steps are the causal steps, I guess the causal part, and then you go into really statistical parts. But as I've mentioned before, to me, it's if you do a really good job, where you're really being very clear about what is your question, what are my assumptions, what is my causal target parameter, what do I need to get causality, and then you're just like, okay, well, I'm just going to throw like linear regression, even though I know that this is not parametric, then what's the point, right? You want to do as best, you want to kind of close both of those gaps as close as possible, and then if at the end of my analysis, I can say, okay, I'm very happy. I really think that there is some kind of a causal thing that I've discovered in it, right? So all of this is causal inference, and it turns out that especially with the statistical part, there is a kind of a line of literature that is very, very rich called efficiency theory that relies very much, and it's kind of derived and driven by things in causal inference, especially in the last maybe 30 years or so. Okay, so let's start going kind of step by step. So the first step would be something just as simple as really understanding your experiment. And this was an actual study that was done, I think maybe 10 or 15 years ago. But the idea was that there was a whole bunch of these national randomized control trials. And they were trying to assess the impact of corticosteroids on mortality among septic shock patients. And this was a very popular question because a lot of people were dying. So it was a question of, do we use steroids or do we not use steroids? I believe this was a question during COVID as well. People still don't know, should we use it, should we not? So there was a whole bunch of studies. And there were 3 big studies at the beginning, and they used kind of traditional method. They didn't really go for causality in it. And it turns out confidence intervals are huge. We're looking at relative risks here. Doesn't look like it's significant, but people were still interested about this. So they did about 29 more trials after that. And then when you kind of do a meta-analysis on it, it seems like, well, now it kind of shifted. We have less variability in these estimates. So it seems like maybe there's a significant effect. And then people did more trials. But can we do a better job being kind of very specific about this question? So let's go through kind of the framework itself. So that's the kind of the setup we might be thinking about. When it comes to what is a target population of interest, so here we have, I think this is for just the 3 of the trials, but 1,300 adults in septic shock. And maybe data looks something like this. This is, of course, a gross simplification of it, but you have a couple of baseline covariates, age, sex, BMI. This is our treatment, the steroid treatment, and then we're looking at 1 month mortality for it. So once again, for this, just think about we have a binary treatment, and then this is some kind of a survival outcome, or you can treat it as binary here. So the next step would be you spend some time thinking about the experiment and so on. So now we're thinking about the causal model and what we really want to learn. So the key part here is to use any type of background knowledge that is available. So by this, I mean confounding, selection bias, measurement error. I'll talk about a little bit of these later on. And then if we know, and it's okay not to know much, usually maybe we hint on something that we know what are the confounders, or maybe we don't, that's fine. We just kind of are being very clear at this step. Now we have these, I'm going to use the idea of structural causal models, and I put kind of a star next to it because once again, you can use a whole bunch of things on this. There are other causal frameworks. Here I'm listing a few of the other ones. For example, the single world intervention graphs. Now I can be more clear about the kind of what the interventions are on those. Decision theoretic, you can just use potential outcomes, so many different ways. The one I showed today, I picked just because it includes a couple of different frameworks, so I can show you a bunch of different things that we can do. And these structural causal models are essentially just a language for expressing the knowledge that we have, and I'll give a couple of examples. And they represent unification of causal graphs, structural equation models, and counterfactual. So I'm trying to cover a whole bunch of things so you get to see it today. So I've alluded to it before, so we have some knowledge, maybe we don't. Usually it's very limited. Maybe we know a little bit about which variables affect each other, what are the unmeasured factors, functional form of these relationships, or maybe I don't know anything. We could use graphical models here to help us find kind of maybe the sufficient set of variables for whatever we're hoping to learn and so on. Or we can just encode causal assumptions in these structural causal models. So what this would look like, there's 3 things that define these structural causal models. The first ones are these kind of endogenous variables. Okay, I give up. These include variables that we measure, but not always. These are usually something that we know about the process. So here we had age and gender and so on. Those are things we know and collect. And they're usually affected by other variables in the model. Then we have these exogenous variables. Those are those U's. They're not going to be affected by other factors in the model to a certain extent. I'll show you the graphs. And they represent the unmeasured factors that are not in X. It is possible that something that's in U can then jump into X if we gain some information on it. But usually we're going to know, they represent some sort of kind of randomness that's in this graph. I don't know much about it. I don't know where it comes from. How is it distributed? I don't know. I have no idea. It's just going to be there. And then we have these function Fs, which is a set of structural equations for each of these X's, which are the things that we know and we collect. Once again, I have no idea what the functional form of those are. I don't care. So these will be 2 examples of structural causal models for what we had. We had W's, A's, and Y's. So then we can see we have kind of a function for each of them. So that's V equals some function W. W equals some function of FW, and then we have that exogenous part to it. So I have no idea what this function is. I'm not putting any form on it. I have no idea. It doesn't matter. And then I'm saying something about there's some randomness in it. I'm saying that my A, which is my treatment, is now some different function, FA, which is now what I take as input is my W's and then some exogenous factor that is associated with my treatment. And then I have my Y, which is also a different function, which takes as input A and W, and then something that's kind of a random part to that outcome. So if I compare it to my other structural causal model, it looks pretty much the same, but now I don't have W in this part of FA. So what am I encoding in these? I don't know Fs. I said there's some random part, something that I collect. So the only kind of information that I have in this one, the information that I have in this first structural causal model is that there is some kind of a time ordering. So the only thing that I'm admitting that I know is that A comes after W, and then Y, it comes after A and W. So it's the only thing I'm saying, right? I'm not saying that there is some kind of parametric form here, nothing. And this might correspond to something that is kind of observational data, right? I think that they're all somehow connected, right? But I don't really know. The second one, I'm also encoding that time ordering, but I'm also saying that my A doesn't depend on this W. So maybe this corresponds to something like a randomized trial. So I actually have more information now in this second structural causal model, because I'm saying that A is just a flip of a coin. It's not in any way determined by my W. So that's the type of knowledge we tend to encode in these. We can go and be a little bit more elaborate. So typically what we have is these U's are also all connected, so there's some kind of dependence through these unknown parts, right, the random parts. Here I'm encoding more knowledge where I'm saying that actually UA is independent on UY, and then I can show it on a graph. And what's really nice about these structural causal models is that I can write it as these functions, but then that also corresponds to a graph. So these are called direct cyclic graphs. So I can have this kind of one-on-one relationship. And the nice part of this is that usually, sometimes you work in a single time point setup, but usually we have much more elaborate processes. So if you think about drawing a graph where everything is collected to everything, this becomes a complete nightmare. So it's really nice that you can kind of jump from a graph. Sure, it's nice to visualize it, but then I can also jump and show it in terms of kind of longitudinal processes and then much more complicated things in terms of these equations as well. So maybe our graph looks something like this. So this is what we had before. I'm not showing the U's here. This is kind of standard in the notation that you don't necessarily have to show it, but it's always there, and we always know that there's a U part that kind of goes into a whole bunch of variables as well. So this is kind of just to remind us. So the only reason why we do this is because we want to represent some kind of a background knowledge. Structural causal models help us. These are just sets of these non-parametric structural equations, or as a graph, which are direct cyclic graphs. We just show what we know and what we don't know, and usually the knowledge that we encode in these is typically the exclusion restrictions and independence assumptions. That's usually what we encode in that. And that's part of a causal model that we write here. So once we've decided what we know, what we don't know, how are we going to go on, now we decide what we're actually going to learn. So I've talked before, kind of the canonical example is this thing called average treatment effect. So now we're showing kind of the causal representation of it. And what I'll always do is usually I'm writing AT here. This is just some kind of a function. P is the probability distribution of that process that we have, which generated our W, A's, and Y's. Once I put a star on it, this is kind of a distribution that lives in that causal model. So that's kind of augmented with these, whatever we had, like right causal assumptions. So every time you see a star on it, just know that that's the causal parameter that corresponds to, it's defined in terms of these, right, Y indexed by 1, but what we observed is just Y. So let's kind of decompose it a little bit. Hopefully this is intuitive. It makes a lot of sense. If you looked at it on a graph, and we looked at this particular kind of factual, if we just kind of forgot about this second part, what we're doing is we're setting A to equals 1, and then we have these two arrows. We have some W's, of course there's some U's as well, and then setting A to 1, it's not random anymore, that points into Y. So this would be kind of correspond to thinking about some mortality of subjects in the population had they possibly, contrary to fact, received steroids. Or we can flip it around and then kind of have the same thing, but if they have not received steroids. So this is what I talked a little bit at the beginning. So this is in terms of kind of the causal target parameter. But what we actually observe is data that looks something like this. And this is why it's often said that causal inference is almost like a missing data problem, because we can see some parts of the counterfactuals, but then we can't see others. So there's a lot of question marks here. And what we really want is we want to connect this to this, right? And then do some kind of estimation. So the causal parameters are functions of this full data. So we have to do something to kind of jump to the statistical part. So what is the connection to the full observed data? So what do we need to actually identify this parameter we're interested in from the observed data? So this is kind of a graphic from it. We want to jump from the counterfactual population P star to the observational population P, which is the one we sample from. And then there's kind of a connection between all of them. But the key step here in the step 3 is that we need to kind of do identification on that part. So for the average treatment effect, it actually turns out to be pretty simple. That's why I like to talk about this parameter. The first thing that we need is this thing called know and measure confounding. It's also known as randomization, exchangeability. It's known under many different names. But the idea here is that essentially my YA is going to be independent on A given W's. So there's nothing else that's kind of can influence this YA. Another thing that's kind of hidden here, and I'm not talking about it too much because we're representing it from the structural causal models, is that I also want that when I give you A, my counterfactual is going to be YA. It's not going to be that I've given you some kind of treatment, but then you're expressing something else. So it's kind of a consistency assumption that's also kind of encoded here through the structural causal models. So that's the first one. And you might say that's a strong assumption, but that's kind of an assumption that's necessary if you want to have causality. The second one, it's a positivity. It's also known as overlap, experimental treatment, assignment, lots of different names. And this one essentially just tells us that this probability of treatment given covariates, so everybody should have some probability of receiving treatment, essentially. So I can't have like a strata where you're not getting it. You have like zero probability of receiving it. That would be a positivity assumption, or in the data, it's sometimes called practical positivity assumption. If I just don't have information, it's very rare in the data to see getting treatment in that strata. So under these two assumptions, yeah, I think we're going to take questions. Oh. Oh, yeah, if there's an X, it's a W, actually. Yes, that's a, there's none. Yeah, there's none. It's X is a W. I forgot to change it. Yeah, if anybody else was confused by that, sorry about that. So this is identification result for average treatment effect. This is about 2 lines, essentially. So if we go, so I don't have a star here anymore, right? So that's my statistical parameter. I'm kind of removing it. So I'm going the other way around to show you. And this is to just kind of simplify. I'm showing it only for kind of the inner expectation, right? So if you just replace this A by 1 or by 0, it would be kind of pretty much the same. It would just be more kind of messier line, more, but it's the same. So I'm just simplifying it here. So if we go from the statistical parameter here, so that's psi, and we kind of write it out. So this is by definition, that's kind of consistency that I talked about. If I assign you A, I'm going to get this counterfactual, this YA, right? So that's kind of the by definition, by the structural causal model, I know that that's how it is. And then by kind of that first assumption that I talked about, now I can just eliminate this part, right? Because all the information, my YA is independent on A given W's, right? So I can write it like this. And then if I'm averaging over all the W's, I get my kind of causal parameter. And then that second positivity one is just making sure that my expectations are valid, right? That I can write these expectations. So that's what is necessary. So for average treatment effect, it's a kind of a 2-line proof, essentially, of going from, once again, from causal parameter to statistical one. So now I have something that's written in terms of the data that I have, and I can think about estimation. So now you can think, well, that's first one, no measure confounding. That seems like a pretty strong assumption. I don't really believe it. So then you can go into kind of more thinking in terms of bounds instead. So I can't identify my parameter anymore without that first assumption, but I can bound it with some lesser assumption. So now I've exchanged my first assumption. So now I'm thinking about, I don't know what this is, but I can think about these bounds, and this is now my parameter. So now I can say, I don't believe this assumption, but I can now bound it, and then I know that my causal effect is somewhere within these bounds. So there's a literature on this as well, which is kind of a different approach to identification. And once again, I'm showing you one framework for identification. You can go through things like do calculus and so on. This is different, but as I said today, I focus on this. So technically, that's the causality, the causal part is now over. I've identified it. We've been very clear about the assumptions. You might think they're strong, they're not. We've been clear about what we know, what we don't know. We know what our target is. We know what we know and what we don't know about the process to a certain extent. What should we estimate? But that first part doesn't tell us how we estimate it. So now we're in a completely functional estimation problem. So we're jumping to the fourth step here. So what we now want is to construct a good estimator. Now we have a hat on it. So we went from a star to no star to hat. And we can construct this using any preferred approach. I'm going to talk about a couple of these today, but mostly focusing on this non-parametric influence function-based approach. So since this is, after all, a machine learning summer school, I would say that I'm going to kind of flip it around. Now I'm going to talk about causal inference needs machine learning. And then in a couple of slides, I'm going to kind of flip it around and see where machine learning kind of needs causal inference. So where does machine learning come in? Of course, not estimators are created equal. Ideally, what we want, of course, is we want something that's preferably low bias, right? And then we want something that has low variance, right? But there's a whole lot of things on the spectrum of it. And we would, of course, like to say something theoretical about these type of properties as well. So if I had to write on a board, so what is a good estimator? Maybe I would write something like this. So I would like to have enable some kind of uncertainty quantification. I would like to say something about the confidence intervals, maybe p-values and so on. We would like to be data efficient, so low variance and consistent. We would like to have a simplicity of a plug-in approach. And what do I mean by that? What I mean is that, for example, if I'm estimating a probability and I'm putting it in some kind of a black box function, I would like it to come out with some kind of what is normal for probability, right? So nothing that's like negative or greater than 1. So kind of what I give it, I would like it to respect the bounds. And these type of plug-in estimators tend to do this, which is quite nice. And I would like it to have some good finite sample performance. So this is what I'm going to use as how I judge different approaches and what I like and what I don't like about them. I also want, and I keep saying this, is I want to do as good of a job as possible. So why do I go through all these frameworks and setups and be so clear if at the end I'm just like, okay, I think this is probably like quadratic, but I'm going to use like linear model, right? So I don't want that. I want to be completely non-parametric. If I know something about parts, then at best I'll be semi-parametric. But I want to kind of address these questions in a big non-parametric model, right? And my true data generating process, which I always denote with this knot here, lives in this big, big space. So those are kind of my criteria for what I want to do. So, so now we can go different directions. So we've done that identification part, and then it turned out that for the average treatment effect, it's going to look something like this. But under randomization, we can actually rewrite it like this as well. And these are kind of the tail of, right, we have two directions now we can go. They're equivalent, essentially, but they're going to lead to different estimators, different ways we go. So we're going to start with this one first. So what we need here is we have the outcome. These are indicators of the two treatments, treatment and no treatment. And this is the probability of receiving treatment equals 1 given W and then the opposite. So if you think about what are we going to need here, well, we're going to need this, right? So we're going to start from that. So if we go back to the DAG and I think about my likelihood, right, we're going to have these three components. These are my truths, and then these are my estimates. These are kind of the usual notation we have in causal inference. I'm sorry, but they're going to be these G's and bar Q's. And also another thing is that usually we don't need all of this. Usually we need a conditional expectation of our outcome given baseline covariates and A's, and that's actually this part. So once again, that really much depends on the target parameter, but usually we work with different means and so on, so that's typically what we need. And for average treatment effect, just remember that's what we need. So for that first tail where we're following that second representation, we need this, and we need to estimate it as this GN. So this leads to what's called an IPTW estimator, inverse probability treatment weighted. And the idea, kind of the intuition behind it, is that we're thinking about confounding as a problem of biased sampling. So this essentially the probability of A equals 1 given W tells us who is underrepresented in our data and by how much they're underrepresented. So if you think of it as a very simple example where we have this population of giraffes, for example, and I have 4 of them, And the probability of whatever treatment is for a giraffe, given W is 0.75, well, maybe I would expect about 3 of them in my treated population, 1 and not. And then maybe if I have something kind of the opposite, then I would have 1 here, right, and then 3 here. So this is kind of an equal population. So what IPTW tries to do is it's going to kind of take that inverse weight, and it's going to downweight all these individuals in the kind of first group, and then it's going to upweight all the ones that are not as equally represented. And then what it's intuitively trying to do is kind of, in a randomized trial, you're kind of equally likely to get treatment or not. So this is trying to upweigh and downweigh, so you kind of have a similar thing. So it's eliminating confounding by kind of weighing you and upweighing you and downweighing you. So that's what it's trying to do. So we can do this as a weighing scheme like I described, but then there's a whole huge literature that talks about, for example, things like matching. What I mean by matching is very similar. It's the same idea, essentially. I'm taking you with your covariates, and I'm saying, so I got treatment, right? And then based on my gender and age, I'm going to find somebody who is opposite, like writes the same, essentially, same gender, same age, given, for example, these covariates that did not get treatment, and that's going to be my pair, essentially. So it kind of tries to match. And this, of course, would be, it's not that simple. It's going to be based on some kind of a distance, whatever you decide, of how many, to me, how many of my counterparts go, so there's a lot that goes into it. I can also match on, you can match on a whole bunch of baseline covariates. You can imagine this is a nightmare the more high dimensional you get. But you can also, for example, match on the propensity score as well. So that's kind of a summary of a whole bunch of information that you have. So that's another thing another way that you can use it. So we can match, we can stratify on these propensity scores, we can weigh on them. There's a whole bunch of things that we can essentially do. So, okay, so let's go back to our list. How does this work? And when I was making that, I gave it the uncertainty quantification, but every time I scratch it out, it just means it's not doing a very good job at it. It's not very efficient. The reason for this is when you divide by something that's very close to 1 or very close to 0, what do we get, right? It explodes, right? I'm weighing by something that's gigantic, right? Or it's very close to 0. So it's very, very variable. It's not really doing a very good job. Doesn't have a simplicity of the plug-in approach, because now we're kind of weighing by things and then taking averages and so on and functions of it. So it's not what I give it and then it spits out something nice. It doesn't this leads to the variance part. It doesn't tend to have really nice finite sample performance. Not always. We can't say things in general, but it's not an efficient estimator. But what's really nice about it, it's very intuitive and very easy to explain and easy to do. So we see this in the literature quite a lot. And as I said, there's a very rich line of people kind of pursuing this, not just propensity score, but matching and so on. It's very rich and very big in causal inference. So what else we can do? We're going back to our graph where we had the parts of the likelihood. Well, we can tackle actually other parts of it. So let's just go for these additional expectations. Once again, that's a little bit of a jump, but the idea is, well, if I'm very interested in what kind of the outcome is and treatment, maybe I know something about this process, right? So that's kind of the other side of the coin. So let's think about this. So I wanted a plug-in approach. So maybe I can do, I don't really need to estimate these, but I can just kind of plug in. This is for the average treatment effect. And I can just learn these bar Qs. I can see what it does when I say my treatment equals 1, when it equals 0, and so on. And then I get some kind of an estimate here. But it turns out that there's problems with how do I actually get inference from this. It's not really efficient, consistent. Once again, it depends if we're actually at the truth and so on. It is a plug-in approach, and fine, I'll give it some finite sample performance. But why is that? And this is a little bit of a deeper dive. Once again, I'm going to try to do it from kind of the highest intuition, but I do want you to understand kind of why this doesn't really work. So naive plug-in estimation, once again, where if I think about estimating all parts, even though I just said that we don't really need it, think about this as a big non-parametric model here. This is where our truth is. This is where my estimate is. And I'm kind of projecting it down so because I want something on the real line, right, which is my parameter. So I want this to be as close as possible here, right? And I want to say something about how variable it is as well. So it turns out that if we think about a specific function class, which is a huge function class, they're called regular asymptotically linear estimators, we can do these nice expansions. Once again, I'm putting a lot of things under the rug here to show you this. But it turns out that we can study the difference between this estimate here, which could be that naive plugin that I told you, that's the truth. And then I can decompose it in some terms. This first term, actually, if this is in a specific class that I just said, regular asymptotically linear estimators, which is a very rich class, I can, this is a really nice term. This is actually going to go to a normal. So this is an asymptotic linearity terms. It gives us a tractable limiting distribution. But there is a second term. There are some parts here that also machine learning is necessary to put this at this particular rate. But the second term, we can't really characterize. It's going to depend on a whole bunch of things. It's very problem specific, your model specific, whole bunch of things. We call this the plug-in bias. This generally doesn't converge at the right rate. And not in all problems, but often this second term is actually going to dominate and be larger than this one, and then we can forget about having kind of understanding what this estimator behaves like. Right. Once again, this is one I'm talking about these estimates we generate them with machine learning. I'm not specifying what kind of architecture or whatever. I'm just saying that I'm being kind of aggressive. I'm not doing this with linear model. I'm estimating it with some kind of machine learning. So the reason why we have this is that we can actually characterize these mathematical things called efficient influence functions. And it turns out that both of these terms and some of the parts in the remainder as well can actually be characterized in terms of these phi functions. These functions, you need to derive them. They're actually quite complicated to kind of come up with, but they're very nice. They're a property of your statistical model, which if it's non-parametric is huge, and your target parameters. So you're gonna have a different phi function for whatever you're trying to study. And every time you have a new problem, you kind of have to rederive them, but they give us really nice theory, and they give us kind of how to think about these problems. And it turns out that once we do these naive plug-in estimation, we can forget about this part needs to be removed. We don't know how to remove it, right? It remains, and then depending on the problem, it will dominate, and we have no idea what just happened, right? It can blow up and so on. So there are many different ways that we can correct for it, right? So we can do that naive plug-in approach at the beginning, but there are other things that we need to do on top of it. And there is literature on this. I'm kind of trying to give you the most modern things in causal inference right now. So what I'll talk about is one of them, even though there's kind of the more canonical one, which is TMLE, but there are kind of more modern methods now as well. Maybe I'll kind of touch on it a bit. Another important thing here is that, so we want to get rid of it because I want to have some kind of certainty quantification. I want to be unbiased and so on. But there's also another thing with these, and this is a property of the target parameter. So things like average treatment effect can actually be what's called double robust. What this means is that now I'm actually going to use estimators that rely on multiple parts of it, both that propensity score, so the probability of treatment given the W's, and that second part, which is the expectation of Y given a whole bunch of things. And the double robust part comes from the fact that if I'm wrong, let's just say that I estimated this and I was completely wrong, right? I'm still okay if I get this right. And then if I'm completely wrong with estimating, right, with this, I'm okay if I get this. So if I'm in a randomized trial, it's quite nice because I can rely on having some knowledge about this. So it's almost like you have two chances to get it right. So this is a property of the target parameter, and then some estimators take advantage of it or not. So of course, you want to use the estimator that potentially takes advantage of it, so you have that extra chance. So the last thing I'll talk about is one of these double estimators that use the double robustness property. And as I said, we want to be efficient. So how do we, now we're kind of pushing it even further, how do we kind of efficiently estimate that average treatment effect on the observed data? So we're going to do two steps. The first one is we're going to create an initial estimator, right, which is at bar Q, using ML. And we're going to be aggressive, right? We're non-parametric. And then we're going to update that initial estimate to achieve optimal bias variance trade-off for the parameter itself. And that's going to give us kind of an efficient, unbiased, finite sample robust plug-in estimator. So So what this looks like, that's step one. Here I'm showing kind of an ensemble learner. Once again, you can put whatever you want here. Maybe I'm using some kind of ensemble learner with cross-validation to get that kind of initial estimate. I want it to be a pretty good one because I do need some kind of nice rates of convergence for that part. And then what I'm going to do next is I'm going to use that function that I talked about before when we went into a little bit of a deeper dive that I said is called efficient influence function, corresponds to the target parameter. I'm going to use that in a clever way. So if you remember, once again have that sphere before, that's the truth, that's the kind of estimate. I'm going to walk in the direction of the maximum change of my parameter, and that is going to be a very, very special direction that I walk in as well. So if you look at the graph that's on the left here, so this is kind of my truth here, and these are two directions I can walk in. So this is kind of a projection, like a 2D idea of it. So this is in terms of a treatment effect. This is kind of a change in log likelihood. So I want to get to the truth, and I want to get there kind of in kind of a big step, to say. So this is actually also a pretty good direction, but it's going to take me longer, right, to get to truth. If I even reach it, it actually turns out that I don't reach it. So this is a very particular direction that I'm going in this high-dimensional space, very particular path that kind of leads me to the truth. So that's one interpretation of it. The other one is that I'm removing that second term, and by that I'm giving kind of that expansion, right? The difference between my estimator and the truth, I'm giving it a tractable limiting distribution. So it's very powerful, and if you ask me like where causal inference is these days, this is kind of where most of us live at the moment. Okay, so now that we've use some kind of estimation step, let's just say that we can get some kind of an uncertainty as we can get confidence intervals for it as well. We're kind of back to our application. So as I said, what's really nice, this type of, for example, TMLE behaves as a sample mean of some function called efficient influence function, and this gives us a nice tractable distribution. So not only do I have an estimate, I actually have a confidence interval, even though I've used some machine learning, I'm not specifying anything at all. And it gives us, because it is efficient, it gives us really nice confidence intervals as well. And then if we reanalyze some data that I've talked about at the beginning, like we can see we have a significant effect and a much more efficient estimate as well. So this is kind of if you go back to that chart for that last estimator I talked about, it's quite nice. But the caveat is, of course, it is more difficult to derive. It's parameter specific. You need to do some math to actually do it. So now we're kind of almost at the end. So now we can kind of talk about interpretation at the end. So we have a whole bunch of assumption, identification, estimation, and now we can think about, okay, so what do my results actually mean? What's the causality of it? And typically what we do as kind of the last step is we kind of rethink the causal bias, what is the gap, right? And we can play these kind of sensitivity analysis games where I'm asking, how would my assumption change if I maybe included more covariates or something about measurement bias, a whole bunch of things. How sensitive my results to this causal bias. We know something about statistical bias already, right? Because we have some uncertainty quantification, but usually we spend some time at the end rethinking under different causal models, how would my results change? What can I say? And then we would maybe plot them across a whole kind of big spectrum. So that kind of concludes. I think I have just a little bit of time, but I want to flip it around with kind of a simple example of where ML needs causal inference. So I'm flipping it around. Hopefully the causal inference needs ML is quite clear, so let's flip it around and think about where does causal inference play a role in machine learning as well. And I'm going to talk about, so this connects to a lot of things that you already covered in the previous lectures. So this is kind of a combination of reinforcement learning and transformers, could be a whole bunch of things. There is a literature in RL, which is called goal-conditioned RL, and there's a whole bunch of things that go into it. Here I'm using one example from a paper by Gaussian from 2021. The idea is that we collect a whole bunch of trajectories, right? That's your actions, states, actions, rewards, and so on. Maybe we have an episodic thing. We collect them and we kind of put them, right? We have a whole bunch of these trajectories. We see what kind of goals they achieved. And now we do something maybe similar to kind of supervised learning when we're saying that we really want to learn something like this policy A given S given that goal, so what we've observed, right? So it looks a little bit like the propensity score, right? So we're kind of learning what was the action given the observed goal that I've already collected in my trajectory. So I'm conditioning on something kind of in the future for that particular action at time point t. So turns to be this topic, which is pretty big in causal inference, called selection bias. And to kind of represent it, here's a very simple example. So maybe our goal is to estimate the effect of some kind of genetic mutation, W, on smoking status A. And I'm going to study this in a population of subjects that have lung cancer. So if I draw a really simple DAG here, I have this W that has no effect on A. So this gene does not affect whether whatever you smoke or not smoke. But you have lung cancer. So it turns out that if I condition on Y, so I'm studying this in the population of individuals who have lung cancer, knowing that a lung cancer patient doesn't smoke actually gives me information about W. The reason for this is that in the absence of smoking status, it is more likely that another cause, for example, W, assuming this is a complete graph, actually causes Y. So even though I don't have any connection between W and A, right, there's no arrow here, they're not associated in any way. When I condition on W, now I have a spurious association between W and A, right? So let's see how that can play out. This can play out in certain graphs, not in all graphs, right? It depends. If you're doing, for example, this type of goal condition RL, and you're thinking about this in a medical application where there's a whole bunch of confounding and things that you don't measure, it turns out that it creates really messy situations. And the reason for this is this. So we might ask, what are some causal biases that can arise in this type of training processes? And can these causal biases lead to a poor policy? So the answer to that is yes. Some intuition for this is that if we think of it as a point treatment setup, and I have a simple graph like this, and to make it intuitive, let's just assume that there are a linear relationship between all of them, and I'm putting just a coefficient in front of them. So this is just to simplify the problem. So I have alpha between S and A, right? Beta 1 and beta 2 for these relationships here. And if you use kind of Judea Pearl's language here, which I didn't mention today, but as I said, it's quite, well, it's not similar, but it's one framework of it. We have this idea of R recoverability. R corresponds to the reward here. So it turns out if I have a whole bunch of these type of processes in these graphs, I actually can't learn this relationship if I condition on R. But in this graph, I can. It's completely fine. So some things I just can't recover from the data if I learn it in some ways. For example, as I said, conditioning on these things, which can be called colliders. So how does that play out in the idea of reinforcement learning? Oh. So what we care about, if I rewrite it as calculus, usually I really want to know kind of what is my expected reward given this state and action, right? And if I wanted this to be causal for some reason, right, maybe I'll do some kind of, I'll put a do on it. And then if you're in a linear model, well, maybe I care about kind of this coefficient here, which is the slope of the regression line of R at a specific time point on AT given this particular state. And then this coefficient then becomes critical for learning the optimal policy, once again, very simplified in a linear model. So it turns out that if you do the math, in this type of graph, if we have something simple like just a binary thing, either I give you action or I don't give you action, right? This partial coefficient in this graph is going to be fine. Doesn't matter if I condition on R or if I don't condition on it. In this one, it's actually going to be trickier if I have some unmeasured confounding, and it can even flip the sign as well. So essentially, it is possible that we have a whole bunch of kind of spurious associations that we create when we do this, unless we know the full graph. So here's like a kind of a simple example where we're completely flipping it, and we can see kind of the behavior of something really simple like a fitted Q iteration as opposed to goal condition RL here, where it really, really suffers if you have even one variable that is kind of a latent variable in this type of system. So here, kind of knowing causality helps us, right? Like we can have really nice reinforcement learning, things that can write to a goal supervised learning is pretty cool in general, but we have to be very careful about what our model is and kind of what is it an actual MDP and what is actually the system, because causal inference here kind of brings to the rescue what are the potential problems that we can actually encounter. So in conclusion, I think we have 5 more minutes for questions after this. I just want to kind of emphasize once again, causal inference is a very rich field. I tried in this hour to give you some kind of a little bit of intuition and maybe what are some of the modern topics and things that we care about in this field. But there are a lot of things I didn't talk about today. I've mentioned very briefly matching. There's many entropy methods, graphical models I didn't mention at all. There's higher order efficiency. There's a lot of different things that's going on. It's a very, very rich field. Hopefully I've given like a nice overview where we need ML to make most of causal inference work. That's both in estimation and identification, but we also need causal inference in ML. So they're, in my opinion, very closely related and then kind of work off each other and work nicely together. And with that, thank you very much. The no unmeasured confounding. Yeah, so that just essentially tells us that all the information in our W's is kind of enough to characterize, right? Like things that, when you think about those arrows, right, we have A and W and potentially U as well, right? We're not saying that there is maybe a B that goes into Y, right, which is somehow associated with them. So what you're trying to say is that if I have all these confounders, so maybe, where's my... It's on the first slide, but I had A, Y, and W was a confounder. I'm just saying that there's no more confounders that are somewhere that I'm not correcting for. Yeah, so conditional on W, yes. Yeah, but that's the counterfactual is independent of A, right? Yeah, but that's what's confusing. Yeah. But this is, okay, so this is the counterfactual YA is already under A, right? Exactly, so this yeah. It's essentially just saying that there's nothing else outside of it, right? I'm already kind of given A, so there's no more additional information in the A, and there's no more additional information in the confounders, yeah.
Any of the models can be wrong, and all models will see wrong.
So one of them can be wrong.
Okay, if any of them, but in what sense? Like,
yes.
One model is a good fit, but it's not well qualified. Is that considered wrong?
So, yeah, I should have been more specific. What I mean is it's in terms of being biased, right? So I can actually still be consistent, right, if I get one of them wrong, but I am not going to achieve things like efficiency, for example. I do need, but it's still nice to be unbiased, right? I can still get, and the point of this is when you do these expansions, it turns out that it's kind of the difference between, right, the propensity score, the truth minus the estimate, times the second part minus the estimate. So if one of them is converging to the truth, it kind of eliminates the other one, right? And I don't have this thing, which is another part, so there's more theory, but essentially just, if one of them is wrong and goes, right, it's unbiased and converges to the truth, it kind of takes the other one with it, even though the other one is maybe diverging and is doing horribly. So that's the intuition behind it.
There was another question there. Okay, go ahead.
Yes.
Yeah, go ahead. Yeah, you.
When you showed the results, I was wondering how did more complex architectures affect the performance?
I'm sorry.
When you showed the results, I was wondering how did more complex network architectures affect performance?
So we tried different architectures as well. I'm trying to remember if there's like more variance in the system, if you're trying different ways of doing, because there's many different ways to doing goal conditioned RL as well. But you always get, I can also, because the policy is so simple, I can also see what kind of policy it's converging to as well. And I can see that it's doing the opposite, right? So even different architectures won't really save it here.
there are no more questions, we can thank the speaker. So this was the last lecture.